Hello everyone, I am Laisa Parisotto, and today I'm presenting the article called Cone Detection with Convolutional Neural Networks for an Autonomous Formula Student Race Car, developed by Eric Island Antonello and I from the Federal University of Santa Catarina. First and foremost, race car competitions provide an environment to develop and test technologies in the field of autonomous driving. Formula Student Driverless is a competition held by the Society of Automotive Engineers and consists in the development of a fully autonomous race car, where both speed and precision are important factors for successfully maneuvering around the track. In this work, we present a camera-based solution to correctly perceive the track boundaries, what consists in recognizing and classifying the objects acquired from the camera. According to Kabzan et al. 2019, this should be done with high accuracy, as little latency as possible, and with minimal utilization of computational resources. For this purpose, several algorithms based on convolutional neural networks address this problem. And in this work, we provide an in-depth investigation of different versions of You Only Look Once, or YOLO, algorithm for cone detection. We summarize our contribution in four main topics. First, providing results on different versions of the YOLO architecture for the detection of colored traffic cones belonging to four possible classes, using the Formula Student Object in Context FSOCO dataset. In second place, we show the influence of the image resolution for achieving a trade-off between accuracy and inference speed. In third place, we present the impact under different image perturbations such as brightness, exposure, blur, and noise. And in fourth place, we reveal the benefit of extra data augmentation for improving robustness to the aforementioned perturbation and also out-of-distribution disturbances. To start the methods section, we first need to define object detections and its performance metrics. Object detection is a fundamental challenge in computer vision, and it consists in the ability to classify objects in images and determine their spatial location. According to Liu et al. 2019, finding models that are highly accurate and also fast in their inference is not trivial. In object detections, there are some metrics used to evaluate the performance of the detectors. The first one, intersection over union, as can be seen in Figure 2, is a similarity measure used to evaluate how well the predicted bounding box overlaps with the target bounding box. And thus, for a given IOU threshold, it is possible to determine the confusion matrix, which is the basis for other performance metrics. Average precision is the area under the precision recall curve computed by average precision at some discrete recall values. In the case of object detection and in this work, the precision is averaged from 0.5 to 0.95 with a step size of 0.05. Lastly, mean average precision, or MAP, is used for multiple classes of objects, and it is computed by taking the mean of the average precision for each class. You Only Look Once, or YOLO, was proposed by Reed-Mon in 2016 and is an object detection method based on convolutional neural networks that combines classification and spatial location in a single pass through the image. And that's what makes YOLO an exceptionally fast and accurate method. The network combines several convolutional layers followed by max pooling layer, and it has two fully connected layers in the end where both class probabilities and bounding box coordinates are predicted. Since 2016, new versions of the network were released with optimizations that improved its performance. And in this work, we consider three networks, the YOLO V3, the YOLO V4, and the tiny version of YOLO V4, which is a simpler version with fewer layers. One of the biggest challenges in supervised machine learning is to have good data sets to train the networks. In the context of Formula Student Driverless competition, there is the Formula Student Objects in Context dataset proposed by Dodo et al. In 2020, which segregate cone classes in blue cone, yellow cone, small orange cone, and big orange cone. The dataset is constantly updated because teams that will to have access to the content must contribute with labeled images through a standardized procedure. These two figures show the distribution of examples of cones for each of the classes in the training and testing dataset. To analyze the experimental result, we have separated the FSOCO dataset in training and testing set, and analyzed over two main metrics, mean average precision, MAP, and inference time. It is important to point out that no frames from the training set were used for the evaluation of the networks. So first of all, we see from this table an overall comparison between the networks, where YOLO V4 showed the highest mean average performance with 76.3%, with an average inference time of 33.2 seconds, and the tiny version of YOLO V4 performs the fastest prediction, with an inference time of 5.2 seconds and mean average precision of 56.8%. The third version of YOLO compared to the fourth version present a faster inference time, but with a worse mean average precision. From these overall results, we wanted to investigate ways to improve YOLO V4 tiny accuracy while maintaining inference time still low. To do so, we train and evaluate this network with input images with higher resolution, what is equivalent to changing the size of the input layer of the network. These results show that by increasing the image input size resolution, it is possible to improve networks' mean average performance while still maintaining a fast content detection time. In section 3.4, we have a visualization of the performance of the networks throughout a test image. The metrics shown in the gradient is the intersection over union, where the bright colors show more accurate detections and the dark color shows worse detections. The red rectangles were objects wrongly detected or not detected by the network. From these images, we can see that YOLO V4 has the most accurate predictions. But also, we can see an improvement in the tiny version by increasing the image input size. As in the first image, the YOLO makes several mistakes on its predictions, and in these pictures there are less mistakes and also a higher coefficients of IOU for those predictions. And finally, the experimental results explore the performance of the networks under special image conditions. These conditions or perturbations could be caused by different weather conditions, darkness, occlusion, or other aspects while the car is driving. In this analysis, it was considered three networks, YOLO V4, YOLO V4 Tiny, and another version of YOLO V4 Tiny, which was trained with an extra data augmentation from the FSOCO dataset. For this extra data augmentation, the network received the normal images plus images perturbed with brightness, exposure, blur, and noise. and that is 5 times the number of normal images that were employed for training. From this table, we can see how the YOLO v4 Tiny with extra data augmentation improved the test performance under those effects. While there were small improvements for brightness and blur, and even a decrease in the mean average performance for exposure, the performance under images with noise was 28.8% higher than the network trained only with normal images. Finally, we also wanted to evaluate how the networks performed with out-of-distribution perturbation, where different classes of objects were set in the images, as well as occlusion. In the first image, we can see that YOLO v4 detected 2 cats as yellow cones. The YOLO v4 Tiny detected only one of those cats as an orange cone, and the YOLO v4 Tiny with extra data augmentation did not classify that object. In the second image, the YOLO v4 detected 2 birds as blue cones, while the Tiny version and the one with augmentation did not detect it. We can conclude that augmenting the original dataset with images under the 4 aforementioned special conditions will to a more robust cone detection method that can ignore these out-of-distribution objects that resemble cones in shape. And finally, from this 2 partial occluded image, we can observe that YOLO v4 can more precisely detect objects that are partially occluded, and that the augmentation in the Tiny version did not made any improvement in this situation. As a conclusion, we summarize 3 topics. First, experimental results have shown that it is possible to achieve a fast inference time while maintaining very good detection accuracy, mean average precision, for the 4 different classes of cones using the Tiny version of YOLO v4 with a higher image resolution of 608 by 608 pixels. Second, image perturbations impact the detection accuracy of YOLO v4, even though this network already implements several regularization techniques, such as data augmentation. And in third place, we show that by explicitly augmenting the training set with perturbed image, we have obtained improved mean average precision for test images under perturbations such as brightness, exposure, blur, noise, new classes of objects, and occlusion, when compared to the YOLOnet training only with the original dataset. Thank you very much for your time, and I am available for answering any question.